Hello everyone, welcome to this session. In this session, I will explain another first order ordinary differential equation solving method which is more accurate rather than Euler method is called Runge Kutta method. In this session, I will explain its theory as well as its Python code. So let's start. In numerical analysis, the Runge-Kutta methods are a family of implicit and explicit iterative methods which include the Euler method used in temporal discretization for the approximate solution of simultaneous nonlinear equations. It is used to approximate solution of initial value problems in differential equations. They are particularly popular for solving ordinary differential equations, say ODEs. The most common method, the Runge-Kutta fourth order method, say RK4, is an accurate and widely used technique. The error in Runge-Kutta methods can be divided into local truncation error and global error. The local truncation error refers to the error in a single step, while the global error is the accumulated error over multiple steps. Here the local error is h to the power 5 and the global error is h to the power 4, and here h is the step size. Let an initial value problem be specified as follows. dy dt is equal to function of t comma y with the initial value y at a point t is equal to t naught is equal to y naught. Here y is an unknown function. It may be scalar or may be vector of time t, which we would like to approximate. We are told that dy dt, the rate at which y changes, is a function of t and of y itself. At the initial time t naught, the corresponding y value is y naught. The function of t and if the initial conditions t naught and y naught are given. Now we pick a step size, say h, which is greater than 0 and should be definite value. This is the formula of Runge-Kutta method, that yn plus 1 is equal to yn plus 1 divided by 6 into k1 plus 2 star k2 plus 2 star k3 plus k4, and tn plus 1, that is equal to tn plus h. Here n is equal to 0, 1, 2, 3 and infinity, using k1 is equal to h star function of tn comma yn, and k2 is equal to h star f of t n plus h divided by 2 comma yn plus k1 divided by 2, and k3 is equal to h star f of tn plus h divided by 2 comma yn plus k2 divided by 2, and k4 is equal to h star f of tn plus h comma yn plus k3, and here yn plus 1 is the RK4 approximation of y tn plus 1, and the next value yn plus 1 is determined by the present value, say yn, plus the weighted average of 4 increments where each increment is the product of the size of the interval, say h, and an estimated slope specified by function f on the right hand side of the differential equation. Here k1 is the slope at the beginning of the interval using y. Say it is a Euler method, and k2 is the slope at the midpoint of the interval using y and k1. And k3 is again the slope at the midpoint, but now using y and k2, and k4 is the slope at the end of the interval using y and k3. In averaging the four slopes, greater weightage is given to the slopes at the midpoint if f is independent of y, so that the differential equation is equivalent to a simple integral. Then RK4 is called Simpson's rule. Here I have plotted f of t, y and versus t graph. Here at point y naught, first we have draw a tangent, and k1 is the slope of this tangent, and from using k1 and y we have draw another tangent, and k2 is the slope of this tangent, and using k2 and y we have drawn another uh, tangent, and k3 is the slope of this tangent, and at the end of the function we have draw another tangent, and k4 is the slope of this tangent. Here the coordinates are shown. I hope this is clear to you. Here I have written some numerical problem based on Runge Kutta methods. The first question says that using fourth order Runge Kutta method, write a Python code to solve the first order differential equation. Say dy dt is equal to e to the power minus 2t minus 3y with the initial condition is at a point t is equal to 0, the value of y is 5, and plot your result using matplotlib and compare that with analytical solution, which is given that y of t is equal to e to the power minus 2t plus 4 into e to the power minus 3t in the same plot. Choose appropriate labels and legend for this. The three questions are almost same. I will solve this question by using Python code, and I hope that you will solve this question yourself after I will show you its Python code. So let's see its Python code. Here it is the Python code. As usual, first I have import some packages. For import numpy as np for defining the function, and for defining the x domain or y domain uh, that you say, and import matplotlib.pyplot as plt for plotting the function. Here I written the inputs, that is t naught is equal to float input t naught. Here t naught is the initial value of the point at t is equals to t naught, and y0 float input y0. Here y0 is the initial value of y at a point t is equals to t naught, and tn float input tn. Here tn is the final value of t at a point t is equals to tn, and n is the integer input. Enter the number of steps. Here n is the number of steps. Then I have taken two empty lists, say a and b, and then defining the differential equation which is given in the question, that def of t comma y, and return np dot exponential of minus 2t minus 3y. And then I have defined the RK4 method, that def RK4. Here I have taken the function name as RK4, and t naught y naught tn comma n, that's the arguments, and here I have written h is equal to tn minus t naught divided by n, and then I have written uh, for loop, say for I in range n, k1 is equal to h star f of t naught comma y naught, and k2 is equal to h star f of t naught plus h by 2 comma y naught plus k1 divided by 2, and k3 is h star f of t naught plus h divided by 2 comma y naught plus k2 divided by 2, and finally k4 is equal to h star f of t naught plus h comma y naught plus k divided by 3. This is the Runge Kutta method's formula, and K1, K2, K3 and K4 are the slopes. Okay, and finally K is equal to K1 plus 2 star K2 plus 2 star K3 plus K4 divided by 6, and here I have put the value of K, that is yn is equal to y naught plus k. This is the Runge Kutta method formula, and I have plug in the value y naught is equal to yn and t naught is equal to t naught plus h, and then I append in the empty list a and b that a dot append t naught and b dot append yn, and finally return tn comma yn. And then I have taken a new variable say result and put in the value of result in RK4 T naught comma Y naught comma Tn comma N and print the solution of RK4, that is results. And then I have written the T domain, that T is equal to np dot linspace T naught comma Tn comma N. Here T naught is the initial point and Tn is the final point and N is the number of points. And then I have defined the exact solution which is given in the question, that is DEFGT, and then return np dot exponential of minus 2t plus 4 into exponential of minus 3t, and then print the value of the exact solution at a point t is equal to tn, that is gtn. And then I have plot this function, that is plt dot plot a comma b and I have also plot the exact solution, that plt dot plot t comma gt and plt dot legend plt dot x label for labeling the x-axis and plt dot y label for labeling the y-axis and plt dot grid for the rectangular grid and plt dot show for showing the function. And I will show you, I will run the code. First, the value of t naught is 0, which is given in the question, and the value of y naught is 5, which is also given in the question. And I have taken the tn value is 1, and the number of steps I have taken as 1000, and run this code. You you will see that the solution of RK4 method is 0.334, and the value of exact solution at point t is equal to tn is 0.334. And you show that the exact solution curve and the RK4 curve is overlapping. In this way, you can say that this is the more accurate method rather than Euler method. It is fourth order accurate method. I think this is clear to you, and I hope you will solve the 3 question yourself. Okay, thanks for watching this video.